Okay, in this second part of this video on vorticity and circulation, um, I would like to go through an example as well as continue with definition of circulation and the formula related to circulation. To summarize what we have discussed so far, we discussed that the vorticity is curl of velocity, which in index notation we can write it as permutation symbol epsilon ijk uk comma j. And this vorticity is, we showed that if we divide it by 2, it is actually angular velocity of the flow. And this is shown by calculating the curl, which gives us this component, and these components divided by 2 is the elements of the Cij, which is the antisymmetric part of the gradient of the velocity. Okay, so let's work out a quick example to demonstrate this. We have a velocity vector given as u, the x component in the xy coordinate system. For simplicity, without losing generality, I will consider a 2D flow defined as given here. And we would like, sorry, this should be velocity. And I would like to calculate the vorticity first. Okay, so I come here and calculate the curl of my u. And here, because this is 2D in the xy coordinates, therefore the curl would be perpendicular to this as a cross product of two vectors, or you can do any way that you feel comfortable to calculate the curl. So we can come here and say curl of u is the determinant of ax ey, and we have for the gradient and the velocity vectors, say u and v. And of course I have to have the ez, although I know that the z is 0. The component in z direction is 0. This will give me 0 for ax, ey for the component of the vorticity, and therefore I will get ez only component, and that would be dv dx minus du dy. You can see this also from here, because if I and j and k go from 1, 2, 3, take these values, then if I is 1, the derivative with respect to z will be 0, and so on. The only component that survives is I3, J2, J1 and K3, K2, or I1, J2, J1 and K2, and therefore we get the expression that we have here. Okay, let's calculate the dv dx. dv dx is the partial derivative of y component of the velocity with respect to x, which becomes y squared plus 4, and du dy, the partial derivative of u component with respect to y, is 2x squared minus 3. Therefore, let's call it omega z component here for the vorticity component. Vorticity, I call it omega, is becomes y squared y squared plus 4 minus, there's a minus here, there's a minus here, so we have to multiply du dy by minus 2x squared plus 3, and this gives me y squared minus 2x squared plus 7. So this is the vorticity. Obviously it is a field quantity. By that I mean that for different values of x and y in the coordinate system, we will get different values for the vorticity. Okay, how about angular velocity? We know that it is vorticity divided by 2, simply. So we come here, and if you like, we get equal to y squared minus 2x squared plus 7 divided by 2. So this is my angular velocity. So as you see here, once you understand and go through the previous video on this topic, and you can relate basically the antisymmetric of the antisymmetric part of the gradient of the velocity with reference to the curl, you will see that you will have a very simple calculation for any field that you are given. 3D is the same, and then you can calculate it similarly. Of course, you will have more than one component in 3D, and then you can take it from there. Okay, so I made the chart of this velocity field. This is the velocity field to get some feeling of it. So as you see here, this is graph between -2 and +2 for x, and -2 and +2 for y, and this is the velocity field that we have, and based on that we calculated the vorticity. This is not the vorticity field, this is the velocity that we started with, and then as you see here, there is a clearly a circulation here that we calculated and kind of fades away in different direction as you go away from the origin 0 and 0. So sometimes it's good to graph these things and get a feeling. Maybe you can do the same thing for vorticity and angular velocity as well, which will take different values based on the values of x and y. Okay, so having said that, we can move on to another quantity, which is circulation. Circulation is basically if you have a flow, let's say you have a flow in a domain, and then you come and say, okay, if I make a, maybe I am picking up another color. If I make an arbitrary closed path like this one in the domain, can I calculate the vorticity which is inside this enclosed path? Basically, you are saying that it's like fishing. You put your net and say how much vorticity I can catch with this net, shall we say. It's a kind of analogy here, but it is very similar. So if you have any vorticity here, that this is called circulation. So how do we calculate it? Is basically we come here and say, okay, if I get the tangent to this field, or shall we say the uh, component of the velocity in the direction of tangent to this field, I can write the circulation as follows. Circulation is usually designated by the capital letter gamma, and then that is the line integral of u, the velocity field, and dl, which is the line tangent to the field. And therefore we get if we get omega here in this field, then this will be non-zero, and if it is zero within that closed loop, we don't have circulation. Let's have a 2D domain for the fluid, and then see what we can get out of this in relation to the omega. So let's have a closed path like this from A to B to C and to D. So this is dx, this is an element, this is my closed path. Let's call it this 1, 2, 3, and 4. At A, I will have velocity u and v in x and y direction. So my u is u and v at point A. Let's look at AB, the line AB, and gives me gamma 1, which is u, the velocity tangent to this path, and the length is dx. For line BC, along this path, I will have v dv dx, because v is here and it will change from a to b by dv dx. So this is my change in velocity, and the path is dy. So this is my gamma 2. Similarly for CD, I will get minus, because I have the direction matters here. I'm going backward, so I get minus u plus du dy, and the velocity, the path is dx. So this is my gamma 3. And finally for AD, again there is a minus v dy. Now if you come and sum up all of these things, so sum of gamma I from 1 to 4 will give us, after some simplification, will give us dv dx minus du dy dA dx dy. And as you see here, this is actually the omega z component of vorticity. So therefore, we can say that our total gamma is omega z dA, which is our elemental area. And this is basically this formula broken down into, 4 simple paths. And this path could be any shape. Doesn't matter what the shape is, as long as you do the the integrand correctly and integrate it, then you have the result that we showed here. And if I want to write it in a more general way, this is u, sorry, I use u and v interchangeably sometimes. This is dl, and this is, and by Stokes theorem you can say that this is actually dA in 3D. As I shown here, that for a simple 2D element we get this thing. So basically this is a general formulation of this case. Okay, so we have discussed vorticity, we have discussed the angular velocity, and we have discussed the circulation, which is basically the collection of vorticity in a enclosed path. If omega is 0, let's say you get, if there is no circulation in your enclosed path, therefore circulation is 0. And that's a good measure of if you have any circulation in your enclosed path or not. Using this has a very useful and direct application in aerodynamics, and that is related to Kata Tchaikovsky theorem or formula. This basically connects circulation, gamma, to lift force on a body in a flow. And specifically, this is has a lot of application, as I mentioned. In it could be anybody, could be cylinder, could be anything, but specifically to airfoil. So if you have the cross section of a wing of a plane, let's say this airfoil, and the flow is passing, or the airplane is moving in a stationary fluid, either way, and then you come here and say, okay, let's assume a path around this airfoil and see how much circulation we can capture. And that's the circulation that basically will give you a lift, will give you a lift, a force upward, so airplane can fly in thin air. And of course there is a drag, but here we are interested in the upward force. I will not go into the fluid mechanics of the lift and drag here, at least, but it could be shown by using Bernoulli or third law of Newton's third law, that you will get a lift and a drag. But we would like to connect this circulation to the lift here. Okay, so this, if I call FL my lift force, is actually rho u gamma. I make an infinity here, which is, I will drop the infinity, but this is the density of the fluid, free stirring. This is your flow velocity before getting close to the airfoil, and this is, as we mentioned, circulation, and this is lift. It's a very simple formula, but kind of misleading because it has a lot to say about calculation of lift. So if around an airfoil you don't have a circulation, you will not have a lift. So that is why the profile of the airfoil is very important. And these two, Kata and Joukowsky, they did this independently with very, a couple of years distance between their publication. But kata is very much used in aerodynamics, and says that the the, the trailing edge of the airfoil, the condition that you apply at this point, the trailing edge, the velocity of the flow which is leaving at the bottom surface of the airfoil is equal to the upper surface. So basically you will have a streamline leaving the trailing edge. That's a condition that usually we apply, and the aerodynamic engineer, when they want to design an airfoil, they do it such that this condition is satisfied, because it will affect the lift and obviously the circulation. Okay, so let's have a very quick insight into this formula that I just mentioned. So let's consider this airfoil. I will draw it again for the purpose of this. I would I will not call it a proof, but it is a rough proof of this formula, which gives you insight. But there is more in-depth calculation that we can do. I will not go through it here, using complex variable techniques and conformal mapping to to map this shape of the airfoil into a circle using complex variable functions, and and then you do calculation and then return it back to the your coordinate system. Let's have this airfoil, and then the median length of the upper surface and lower surface, let's say call it C, uh, and what we do here is when the flow is passing through this airfoil, let's say we have a velocity u at the bottom, and obviously because of the shape that we have here, more chamber here or more curve on the top, we will have u plus delta u, because according to Bernoulli, because we have u plus delta u, we will have say a pressure P here, and because this u is smaller than u plus delta u, we will have a pressure difference. And basically the pressure difference is responsible for creating this lift. So we have in an airfoil, in an airplane, you will have a higher, if you measure in the lab obviously, if you measure the pressure in the beneath the airfoil, you will see a higher pressure compared to that of the upper side of the airfoil, and reversely for the velocity. Velocity is lower at the bottom and higher at the top. Okay, so let's calculate the circulation. Therefore, circulation would be gamma. On the upper part, I will have u plus delta u times c. Remember, the circulation was the velocity tangent to the path that we have, and this is our path here, minus, because we have a closed path here, minus uc at the bottom. So this is at the top, this is at the bottom, and we consider c as an average between these two, so we don't need to consider the detail of the length for each path. So we consider c, which is the median of these two. So this becomes c delta u. This is the circulation. Now let's apply Bernoulli. Bernoulli gives us, we get the pressure uh, on the top side plus half of the rho velocity square is equal to the pressure at the bottom. Bernoulli is basically conservation of energy, half of the velocity. If you simplify this, and you will get delta P is rho u delta u, ignoring second order terms. We assume that delta u is very small compared, therefore delta u square can be ignored. Now lift, as we said here, lift is rho u gamma. this becomes, sorry, yeah, let me write it again. Rho u gamma is rho u, and gamma we just calculated C delta u, right? So this is my gamma. Actually, maybe it is better to do it from what we know. We can say that my lift force is actually the C, the median chord, C delta P. Because as we mentioned, is the difference between these two pressure. If you like, I can write it P plus delta P minus P. So this is my lift. And therefore I come here and substitute for my delta P as I calculated here, which is C rho u delta u, which I can write it as rho u C delta u. But delta u I just calculated is actually gamma. And then I get my formula rho u gamma. So this is a very kind of rough calculation. As I mentioned, there are more rigorous way of coming to the same conclusion, but the formula stands, and then it is used in aerodynamics. For reference, just to finish this, for reference, or at least one of the references, you can use fluid dynamics by Varsi ZUA CRC publication 1993 or a newer version. And that is it for this series. We discussed some background, some flow kinematics. We started from flow kinematics. We defined and calculated vorticity, and also the, maybe I can add here the vorticity and angular velocity. We defined and calculated circulation and Koto-Joukowski equation. Thank you.